Hi guys, so hopefully your revision is still going okay and hopefully you're getting ready for the upcoming exams. So in today's video, we're going to look at projectiles. So we're going to do a summary of all the key projectiles formulas that you can use in mechanics. So obviously, what I'm gonna do in this video is I'm gonna go for a lot of calculations and formulas using letters rather than numbers. So it may get a bit heavy, may get a bit full on. But if you can follow all of these calculations and all of these formulas, then you should be fine with projectiles because I'm basically going to summarize the whole topic. I'm going to go through a summary of the whole topic. And then finally, right at the end, we're going to go through how we can actually make the model more realistic. So sometimes you get questions saying, like, give 2 refinements to the model to make the projectile model more realistic. So I'm going to go through that as well at the end. But the first kind of 4 key points I'm going to go through today is how we can use Suvat to get an equation for the motion of the particle. Secondly, I'm going to go through how you can calculate the maximum height of the projectile. I'm then going to go through how you can calculate the time it takes to reach the maximum height. And then I'm going to go through the final velocities, how you can calculate the final velocity of the projectile once it hits its target over here. So imagine you've got this kind of scenario here where you've got a ball and you're going to kick a ball from a height of h1 meters above the ground. So that h1 could be 0. I mean, it could be any number you like. Could be 10 meters above the ground, 0 meters above the ground. It doesn't really matter. It's just some kind of height there. And then you're going to kick the ball and it's going to hit this target here, which is h2 meters above the ground. So again, it could be 0. So it could be a flat projectile, a flat standard, golf ball kind of projectile, or it could be one of these kind of diagrams where maybe you're like 10 meters above the ground, you're going to kick the ball and you've got to get it so that it's like, for example, 20 meters above the ground. So you could get a question like that. So let's try and use Suvat to try and get some equations for this motion here. So remember, when we start off with these projectile calculations, the key formula that we're going to use is this equation. So the Suvat equation, S equals ut plus half at squared. So generally, when you do these projectile questions, that Suvat equation is always your starting point. So that's the equation that you want to pick. Now, because we're moving in 2 dimensions, so you're moving, so imagine if you've got like, like the sorry, let me do this in blue here. So imagine you've got like, the x-axis there, the y-axis there. We're moving in 2D. So technically this is really a vector. Projectiles are really vectors, to be honest with you. We're doing 2D motion, so we do Suvat in both directions. So that's how we deal with these projectile questions. So we start off by doing the S equals ut plus half at squared equation in the horizontal direction. And before we do that, let's just think about our initial speed. So what I've done with this diagram here is we're going to call the initial speed u. I'm going to call it capital U as well. So that's going to be our initial speed. So the initial magnitude of speed is going to be u. So if we just focus in, if we just like zoom in, sorry, let me go back. If we just like zoom in to the diagram there, that's kind of what I'm doing over here, just zooming in, right angle triangle. So this horizontal initial speed is going to be u. Actually, do you know what? I'm just going to make this u there a capital U just to be very, very clear. So we've got this component, this horizontal component, u cos theta. So remember, cos is adjacent over hypotenuse. So therefore, your adjacent is your hypotenuse times cos. Similarly, with this initial vertical speed, so that's going to be u sine theta. Okay, so now if we're going to do this S equals ut plus half at squared equation in the horizontal direction, let's fill in our letters. So S is our width, so the distance we travel. So if we go back to our diagram, what we're going to say is we're going to travel a distance horizontally of W. So our horizontal distance, our horizontal displacement will be W. So to go from our starting point to the target, so we're going to call this point here the target. So that's the target. So to go from the starting point to the target, the S value, the displacement is W. Okay, so let's write that in there. So capital W. Now our initial speed is going to be u. So our initial speed horizontally is going to be u cos theta. So u cos theta horizontally. So horizontally. Now acceleration in the horizontal direction always 0. So there's no acceleration horizontally. So with these projectile questions, we never have horizontal acceleration. And the time, I'm just going to call that capital T. So let's just call that capital T. So what I like to do with these questions, especially the questions you get, the harder ones where they say like, you know, show that this formula is true, generally a good rule to follow, if they don't give you the time of flight, so the time it takes to get from, so this capital T is the time of flight. Let me just make that very, very clear, because I don't want to confuse you guys. So I'm going to call T the time of flight. So the time it takes to get from there to there, that's our time of flight. Okay, so yeah, so a good idea with these questions, if they don't tell you what that number is, just call it capital T. That's what I like to do. So now what we can do is use our equation, S equals ut plus half at squared. Our S is going to be W, and that's going to be equal to U. So our U is this capital U cos theta, capital U, sorry, just make this look more like a U. So U cos theta, and then times by T, so this time there, and then plus, well, plus a half of the acceleration, but that's just 0 anyway, and then times by the time squared, so that's just 0. So therefore we're going to get that W is equal to U cos theta times by the time. So your horizontal distance is always equal to U cos theta times by the time of flight. That's always true there. Sometimes what I will say as well, just because it's on my mind now and I don't want to forget this, sometimes you get questions where they say that the ball must travel at least W meters. So sometimes they say, right, so you're going to kick the ball, it must travel at least as far, at least as horizontally as W there. So it could do this, could do that, could do this, could do that, but it can't do this. So it can't like miss the target. So sometimes you get questions like that. So if you got a question like that where it said, right, so the ball must travel at least a horizontal distance of W, then you need to use inequalities instead. So instead what you would say is, you would say for that kind of calculation, you would say that W must be less than or equal to U cos theta T. Okay, so remember, W is your width, but you want your displacement to be bigger than or equal to that. So you want your U cos theta T to be bigger than or equal to the width. So this width there is a fixed number, but you want to get a target at least as big as that. So you want to get these blue lines here. You could do that, you could do that, you could do that, you could do that. So your U cos theta times T has got to be bigger than W. So if you get a question like that, just bear that in mind. You just have the inequality sign there. So all the calculations remain the same. You just keep the inequality sign there. Okay, so now let's go to Suvat vertically. So remember, if we go back to our diagram, what is our displacement vertically? So we start from a height of, I know I've made a bit of a mess with this now, but let me just rub out my blue lines because yeah, so we can see what's going on. So what is our displacement vertically? So in our journey, starting from, and remember displacement's a vector. So in our journey starting from there to there, what is our horizontal displacement? So what is the distance going from there to there? What is our horizontal, so horizontal displacement? So what would that be? So it's going to be H2 take away H1. So the gap between H2 and H1. So this gap there, so this gap is H2 take away H1. Okay, so your final height take away your first height, that's always your displacement vertically. So it could be negative, be aware. If this height 2 is actually like down here, for example, so if that was your height 2 there, then you're going to get a negative displacement. That's perfect, that's fine, because you can have negative displacements. Displacement is a vector, so you can have negative displacement. So just be aware of that. So your displacement vertically is always the difference between your final height and your first height, depending on the question. Again, your initial speed vertically is going to be U sine theta. So remember, let's go back to the diagram here. U sine theta, your initial speed vertically. What's our acceleration? So now negative g. So remember, again, acceleration is a vector. It has magnitude and direction. Acceleration always goes against. So if we're starting off with a positive speed, so we're going upwards, acceleration is always going against us. So our acceleration is going against the motion. The gravity is trying to pull us downwards. Acceleration is negative. It's going against the fact that we're trying to go upwards. So upwards is positive, downwards is negative. G, our acceleration is negative g. And the time is, again, this capital T. So, I mean, the time it takes to get, the time it takes to go from here to here is the same as like the time we got before. So the time of flight is the time of flight. So the time it takes to do this horizontal journey is the time it takes to do this vertical upwards and downwards journey. Sorry, let me be a bit more clear. Upwards and downwards to there. So it's the same time. It is the time of flight. So it's still this capital T that we had before. And what we can actually do is we can say, well, okay, well, capital T, if we look at the formula we got down here, capital T is actually, I mean, we'll just write this over here. Capital T is equal to W divided by U cos theta. Now, if we had the inequality sign there, now if it was like one of those inequality questions that I was talking about before, where you want to travel at least W meters in the horizontal direction, then your T would be so it's going to be bigger. So let's just divide both sides by U cos theta. So we get W divided by U cos theta is less than or equal to T. So just be aware that if you want to travel at least a width of W meters, then your time would be bigger than or equal to W over U cos theta in this case. But in the standard case where you're going from this position and you want to specifically hit that specific target there, obviously we got the equal sign. So I'm just going to write the equal sign there. So we got T is equal to W over U cos theta. So again, using our Suvat equation, so S is going to be H2 minus H1, and that's equal to U times the time. So it's going to be equal to U sine theta times by the time, which is W over U cos theta. And then plus, so then plus, I'm going to have to write it down here, plus a half times acceleration negative gravity, so negative G, and then times by the T squared, so time squared, so this W over U cos theta all squared. So we get kind of like this this big equation here essentially. That's kind of what we're getting. So what we're going to do on the next slide is I'm just going to copy out this equation again. So point number one, so section number one in this video. So combining results into one equation. So what we're doing here is we're combining this vertical Suvat with this horizontal Suvat to form one equation. So I'm just going to copy out the equation, this equation there that we got. So we got the H2, so H2 take away H1 is equal to, again, this U sine theta, and then times by this W times by W over U cos theta. So I'm just writing it in a neater form. And then we've got minus, so remember we've got plus negative gravity, so we've actually got a minus sign now. So minus G over 2, so a half G, and then W over U cos theta squared. So that's going to be W squared over U squared cos squared theta. So we're squaring that, and we're also squaring the bottom. So we're squaring the U and we're squaring the cos theta to give us a U squared cos theta. Okay, so what can we do now then? So what we can actually do is we can actually multiply everything in our equation by, well, actually, first and foremost, let's just cancel out the U there. We got a U there and a U there. So that's what we can do. So we can actually just cancel that out. So get H2, take away H1 is equal to, now what we've got here is you've got sine theta over cos theta. So remember, sine over cos, that's tan. So we can actually say that this is tan theta times by W. In fact, what I'm going to do is I'm going to write the W at the front there just to make it look a bit neater. So we've got W times tan theta. And then we're going to take away, so remember this G, actually, I'm going to write it like this. So I'm going to combine this second part into one fraction. So we've got G W squared, so top times top, and then bottom times bottom, so 2U squared cos squared theta. Okay, so what I'm going to do now actually is we've got this cos squared on the bottom of a fraction. And what I'm going to do is I'm actually going to write it like this. So remember that 1 over cos squared theta is the same as sec squared theta. So remember, 1 over cos is sec from pure maths. So 1 over cos squared is sec squared. So therefore, what I'm going to say is that we've got H2 take away H1. So the displacement vertically is equal to W, so the horizontal distance, times by tan theta, take away GW squared over 2U squared, and then times by sec squared theta. So the 1 over, so this like 1 over cos squared here, so this 1 over cos squared, obviously we don't need the 1 there, is sec squared. So I'm just writing it like this instead. And let me just be clear, this is a u, not a v. Okay, right, so we got that. I'm just going to make my writing, again, smaller. Oh, no, I didn't mean to do that. Right, let's try that again. Moving my writing up like that. Okay, so then what we get, so we can actually now use a trig. Well, first and foremost, I'm actually just going to get rid of this fraction here. I'm going to times everything by 2u squared to get rid of the fraction. So times everything, let's just put this in brackets here, times everything by 2u squared. So we don't have to deal with any of these fractions. So we're going to get on the left-hand side 2u squared times by h2 take away h1. So h2 take away h1. And that's going to be equal to 2u squared w tan theta take away g w squared sec squared. Now, remember one of our trig identities. So let me just put a box around this here. So remember our trig identities from pure maths. So remember 1 plus tan squared theta is equal to sec squared theta. So remember that identity there. So what I'm going to do now, instead of writing a sec squared theta, is write 1 plus tan squared. So therefore, we get 2u squared times by h2 take away h1 is equal to 2u squared w tan theta take away g w squared times by 1 plus tan squared theta. So what we're going to get, if we just keep on simplifying all this, is we're going to get some equation involving tan. So some equation involving tan. So we're going to get 2u squared h2 take away h1 is equal to 2u squared w tan theta, and then minus g w squared, and then minus g w squared tan squared theta. So then what I'm going to do is I'm just going to rearrange this so that it kind of looks like a quadratic in tan theta. So I'm just going to add the gw squared tan squared to both sides. And then I'm going to take away this 2u squared w tan theta from both sides. And I'm going to add this gw squared to both sides. So I'm going to get a 0 on the right-hand side. So we're going to get gw squared tan squared. So I'm adding this negative gw squared tan squared to both sides. I'm then going to take away this from both sides. So we're going to get minus 2u squared w tan theta. I'm then going to add this to both sides. So add a g w squared. And then I'm just going to copy what we've got there. So plus 2u squared times h2 minus h1. And that's all equal to 0. So all of this, I'm just taking away all of this on both sides of the equation and moving it to the left side of the equation, so that we kind of get a neater equation, and that's a 0 there. Okay, so what we've got here is you've actually got kind of like a quadratic equation in terms of tan theta. I mean, obviously, again, it's not a quadratic, but it's a quadratic in tan theta, because if we just, I mean, if we call, so let tan theta equal x, then what we get is we get gw squared x squared, so gw x squared take away 2u squared w x, and then plus this like constant at the end there, so gw squared plus 2u squared times h2 minus h1 equals 0. So we get kind of like a quadratic equation there in terms of tan theta. So that formula, you can use that formula basically to for any projectile question you like. So that formula is always true. Obviously, don't bother learning that formula. But if you were to get a question ask you to to prove a certain result, you could do that. So let's say that you had like a normal flat projectile where your h1 is 0. So let's just pretend that's 0. So you're on the ground, and let's pretend that your target is also on the ground too. Then what would happen if your h1 and your h2 are both 0, so both your targets on the ground, is that this term there would disappear, so you don't have to worry about that term. And then you get a nicer looking quadratic without that term at the end there. So you just get GW squared times tan squared, take away 2u squared w times tan theta, and then plus this GW squared equals 0. So you can use that as well. So that's again, you don't need to worry about learning all that, but I just wanted to show you how you can use, Suvat to get these equations, these kind of results that that you could be asked to prove in the exam. I don't think you'd be asked to prove something like that, obviously, but I think as long as you can follow that process, I think it's very good that you can see how that process works. So let's move on from this. Now, let's look at calculating the maximum height of the projectile above the ground. So how are we going to do this? So remember that a maximum height, we're talking about vertical motion. So height above the ground is a vertical object. So maximum height is a vertical object. So we need to use Suvat vertically. So Suvat vertically. Okay, so what is our initial speed vertically? So this was the initial speed we had before, wasn't it? So it was u sine theta. And what about our final speed vertically? So we're doing this journey where we're going from there up to there. So our maximum height there. That's our maximum height. So what is our final speed once we reach our maximum height vertically? It's going to be 0. So imagine you throw a ball in the air. It gets to its biggest height. So you're going to throw it up, gets to its maximum height. So you're going to throw it up, gets to its biggest height, and then it stops, isn't it? So it momentarily stops and then comes back down again. So your final vertical speed is going to be 0. Obviously, you've got acceleration going downwards as well. So you've got your negative gravity pulling you downwards. So to find our maximum height, obviously height, we're talking about displacement. Again, we're going to do Suvat vertically. So we've got an initial speed of u sine theta. We've got a final speed of 0 vertically. We've got an acceleration negative g. We want to find the s, the displacement, the maximum height, which is, again, a displacement. So we're going to use the equation. So we've got u, v, a, s. So the equation that's missing t, isn't it? So we're going to use the equation v squared equals u squared plus 2as. Okay, so v squared, well, that's 0 because, 0 squared, 0. U squared, so that's going to be u, capital U squared times sine squared theta. So squaring this number there, you get u squared and then sine squared. And then plus 2 times negative gravity times by your height maximum above the ground. So this s there, we'll just call this height maximum, so our maximum height. Okay, so we get that maximum height. So therefore, then what we get is 0 is equal to u squared sine squared theta, take away 2gh max, so your maximum height. So therefore, so what we're going to get, so making h max a subject to the formula, you get adding the 2gh max to both sides, you get 2gh max is equal to u squared sine squared theta. Divide both sides by 2g. You therefore get that your maximum height is equal to u squared times sine squared theta divided by 2g. So, I mean, if you want to, it's not a bad formula. So, I mean, it's not as horrendous as the formula that we got back here. This kind of like, I call this equation here the projectile equation. So this is this equation there, or well, really technically this equation there is what I call the projectile equation. Sorry, let me get rid of this dash there. There shouldn't be a dash there. So this is the equation which is true for any projectile in the universe. But this equation here is a much nicer equation. So the height for your maximum height. So you can kind of, if you want to, learn that equation, but you don't have to. I mean, what you need to understand is the process. And obviously, when you do the exam, you need to be able to demonstrate the process. But you can always check your answer at the end because this is the formula for the maximum height of a projectile. Okay, so let's go to the next slide. So yeah, so as we just said, so the maximum height is u squared sine squared, so sine squared theta over 2g. That's the maximum height that a projectile travels. But now I've just realized a mistake that I've made, because remember that we are already h1 meters above the ground. So this is a mistake that I just made. I've just realized I made this mistake. So remember, if we're some meters above the ground already, remember that we need to add on this extra initial height. So remember to add on the initial height that we start off with. So don't forget that initial height as well, because that's obviously really important. So your maximum height is going to be this, but plus your h1. So plus your initial height, whatever that may be. So if it's 0, obviously it's just 0. But if it's something else, then obviously, you know, add that extra height on. So don't forget that initial height that you're starting with above the ground. So that's really key. So that's your formula there. Okay, so now calculating the time a ball takes to reach the maximum height. So again, this is another Suvat problem. It's another vertical Suvat problem. So remember our initial speed vertically, again, that's going to be this u sine theta. Our final speed vertically, again, it's still 0 because we're trying to go from there up to there. Acceleration, again, negative g. And we want to find the time. That's what we want to do. So again, this is just normal, oh, sorry, let me go back. Normal Suvat. And the equation we're going to use, so the one that's missing s, is going to be this equation, isn't it? So v equals u plus at. So final speed is 0. That's equal to u, so this initial u sine theta. And then plus, so, well, a is negative, isn't it? So we've got a negative g there, so negative g. And then times by the time, so I'll call this time, let's call it time max. So I don't mean the maximum time, I mean the time it takes to get to the maximum height. That's what I mean there. So we'll call this time max. So rearranging this, we get g, time to get to the maximum height is equal to u sine theta. So therefore, the time it takes to get to its maximum height is going to be u sine theta over g. So that's another formula as well. If you want to learn that, you can. Again, you don't have to. As long as you understand how to do the Suvat procedure, that's fine. So that's the third kind of point that I want to make in today's video. Now, the final speed of a projectile. So sometimes you could get a question which asks you to calculate the final speed that a projectile is going. So this is how we would do this. So what we're going to do, again, we've got our setup here. So we start a height of h1 above the ground. We want to get to this platform here, which is a height of h2 above the ground, and we're going a horizontal width of w. So let's zoom into this part here. Let's zoom in. So we've got kind of this final speed here, this v, which is our final speed. And then we've got our components here. So we've got like our horizontal final speed, so final speed horizontal. And we've got our final speed vertically like that there. Okay, so what we can do is we can obviously, you know, if we want to calculate final speed, remember speed is a scalar, so it's a magnitude, so you want to use Pythagoras. So your final speed is the square root of your velocity horizontally, so I'll just call this VH there. So the square root of your V horizontal squared plus your V vertical squared, just by using Pythagoras. So I call this velocity, final velocity vertically. Okay, so let's look at how we can do this. So, I mean, obviously to get this calculation, obviously to work out the speed, we're going to have to work out our final speed horizontally and our final speed vertically. So how can we do this? So Suvat horizontally. So let's go back to Suvat horizontally. So remember, again, we go back to our diagram. What's our horizontal displacement to go from there to there? Well, it's W, isn't it? So it's W. What was our initial speed? So again, horizontally, the initial speed is U cos theta. And then our final speed is what we want to find. So I mean, this is our final horizontal speed, isn't it? So I'll call this VH. And then our acceleration horizontally, remember that's just 0. Okay, we got no acceleration there. So therefore, what equation can we use? So the Suvat equation that has no t in it. So that's again this equation here. So v squared equals u squared plus 2as. So your final speed horizontally squared is going to equal u cos theta all squared, and then plus, well, the acceleration is 0, so we actually don't need to worry about this part there because that's just 0. So we're going to get that VH is equal to u cos theta. So that's no surprise because the initial speed horizontally, so the initial horizontal speed is actually the same as the final horizontal speed. No surprise because there's no acceleration. If you don't accelerate, well, you're going to stay at the same speed. So that's no surprise. Now, this one's going to be a little different. So when we do Suvat vertically, there is going to be a little bit of a difference. So let's go back to our diagram. What is our vertical displacement? So remember, it's the gap between our final height and our starting height. So remember, this gap there is H2 take away H1. Okay, so we got H2 take away H1. So we'll put that there. So that's our horizontal displacement. what is our initial speed vertically? So that's u sine theta. Our final speed is what we want. So this is our VV, our final vertical speed. And our acceleration is now negative g. So again, it's the same equation we just used. So v squared equals u squared plus 2as. So the v is again this v squared, and that's going to be equal to the u sine theta all squared. That's going to give us u sine squared theta. And then plus 2 times negative gravity, so we're going to get a negative 2g, and then times by this this h2 minus h1, our displacement there. So our final speed in this direction here, this vertical direction, is going to be the square root. So u squared sine squared theta minus 2g times by h2 minus h1. So yeah, that's going to be our so our final speed in the vertical direction. So I mean, what we just want to be careful of, I mean, obviously when we take a square root and when we take a square root of a velocity, it could be either positive or negative. So this could be either the positive or negative version. I mean, it doesn't really matter with this question here. I mean, what we would have to do with our diagram is we'd have to look at whether the velocity is going downwards or whether it's still going upwards. I mean, if you're falling down onto a target here, then obviously your final vertical speed is going to be going downwards. So this would actually be the negative square root of this value there. So let me try and explain this a little bit better. So let's say you've got a projectile, you're starting from there, you're going like this, and you know your final speed's there. If we just zoom into this bit here, so notice that you're still going upwards. So you've still got your horizontal speed in this direction, but you're still going upwards. Your vertical speed is still going upwards. So in that case, you would take the positive version. So this would then be a positive VV. However, if you had like the diagram we had before, which was kind of like this, where we're going, sorry, let me do this a little bit better. So we're going up and then down. Then if we just zoom into this bit here, so now your final vertical speed, so your horizontal speed is still positive, still going to the right, but your final vertical speed, so your VV is now negative. So now we're going downwards, we're going in the negative direction. So just be aware of that. I mean, if you want to calculate a final speed, it doesn't matter, because regardless of whether it's positive or negative, when you do your Pythagoras calculation, so when we do like this Pythagoras calculation, it's really irrelevant whether this is positive or negative. It's really irrelevant, as you'll see now. So let's just go to the calculation that we want. So our final speed is going to be the square root again of our horizontal final speed squared plus our vertical final speed squared, and that's going to be equal to the results we had before. So this here, so this u cos theta. So u cos theta squared, because actually we want b squared. So it's going to be u squared. So u squared cos squared theta. So remember our v8 squared was this there. So we're just copying that. And then plus our vv squared. So it's actually this here, isn't it? So this result there. So again, regardless of whether that's a plus or minus sign, it's really irrelevant with this speed calculation, with this final speed calculation, because that's our vertical final speed squared there. So we're just going to copy that there. So plus u squared sine squared theta, and then minus this 2gh, 2g h2 take away h1. Okay, so now we can actually just simplify this a little bit, because you may notice a trig identity. So you may notice that what we've actually got here is we've got u squared. Let me just do capital U instead. So u squared, and then times by, if we just factorize out the u squared times by cos squared plus sine squared, take away this g, 2g h2 minus h1. Now, obviously, cos squared plus sine squared, this is equal to 1. So hopefully you definitely know that identity by now. So we're going to get the square root. Sorry, let me just move everything upwards. So your final speed is going to be the square root, the positive square root. So of course, speed is a scalar, it's a positive number. So it's positive square root of u squared minus 2g h2 minus h1. So that's going to be our final speed. So of course, I mean, if you're doing like a normal projectile where you just on the ground, you hit it on the ground there, well, your final speed, well, your h1 there is 0, so your initial height there is 0 above the ground. Your final height there is 0 above the ground as well. So this would actually just cancel out, and you just get the square root of u squared, which is u. So if you had like a symmetrical projectile like this, your final speed is going to be equal to your initial speed. Obviously, because you're doing a symmetrical projectile. But with the diagram we had here, where we had like, you know, some kind of height there, and we're trying to get up to this level here, then your final speed is going to be a little bit different to that. It's going to be this here. So the positive u squared take away 2g times by your second height, take away your first height. That would be your final speed. So just note as well, obviously, you know, in order to take a square root of a number, this number inside the square root must be positive. So in order for you to actually get to your target, you just obviously we need to make sure that the u squared is bigger than this 2g times by h2 take away h1. So if that number were to be smaller than this number, then you'd get a negative number inside your square root, which is obviously impossible for these kind of mechanics questions. So just be aware as well, they could ask you a question saying, you know, for which values, so when is this final speed valid? Well, it's only valid if u squared is bigger than or equal to 2g times by h2 minus h1. Because if this number there is bigger than that number, then you get a negative number in your square root, so you don't have a final speed. So your final speed is not defined. So in other words, you don't hit the target, basically, is what that means. So you don't actually get to this target here. So if you kick your ball up there, if this number was to be bigger than your initial speed, it just means you don't hit the target. So that's why that works, basically. So that would be your final speed if you hit your target there. Okay, so that's that. Now, finally, I know this has been quite a long video, refinements to the model. So they always like to ask this kind of question, you know, what refinements can you make to the model? Obviously, you could include air resistance. So that's the standard one that I think everyone uses. So include air resistance. Another one as well. So remember with these projectile questions, we model the balls or these objects as particles. So we don't actually model them as actual like shapes. So you could model it as a sphere. So you could actually, you know, incorporate the, you know, the 3D dimensions of a sphere into your model rather than just like a dot particle. So that's another thing you could say. Another good one, I like to use this one in my answers. So include the effects of rotation and spin. So if you kick in a ball, there's going to be a rotational effect. There's going to be spin in your motion. Obviously, you know, with A-level maths, you don't learn any of that kind of stuff. You know, that's kind of more university stuff. But you know, you could, you know, if you knew that kind of stuff, you could include the rotation effect as well. And lastly, include the effect of 3D motion or 3D forces such as wind. So obviously, with these projectile questions, let's just think about it. You know, these projectile questions, we're moving in 2D. Now, in real life, you know, if you're kicking a ball or like you're hitting a golf ball, you're moving in 3 dimensions, aren't you? So obviously, you're moving like, you know, let me try and draw like a rough diagram. Maybe you start your ball there and you're going to kick it in 3D. So that's like your x-axis, your y-axis, your z-axis. So I know that's a bit of a messy diagram, but generally speaking, obviously in real life, things are 3D. So 3D forces such as wind, obviously wind is not 2-dimensional. You could have like a 3D wind force. So that's a good one that you can use as well. So those are kind of like the 4 key points that I like to make as well with these kind of questions. So yeah, that's just 5 points, 5 kind of I guess, yeah, key points about the topic of projectiles. I'm just going to go back to this really big horrible equation back here. So yeah, this equation here, and I'm going to put a red box around this. So this equation there is always true for any projectile that you like in A-level maths. Now going back to like this step of the calculation here, so this actual first step here. So if you had a question like this instead, you could write this like this. You could say H2 take away H1 is equal to sine theta W over cos theta. So I'm just copying out this top bit here, and then take away G W squared over 2u squared cos squared theta. So instead of like, converting this to tan like I've done there and converting this to sec squared, you could actually multiply both sides by this 2u squared cos squared. Now, if you were to do that, I know I'm running out of room a little bit, but let's try and fit this in down here. So if you were to do that, you get h2 take away h1, and then times by 2u squared cos squared theta. So I'm just multiplying this by 2u squared cos squared, this by 2u squared cos squared, and this by 2u squared cos squared. So if you were to do that, then you get that this is equal to, so sine theta times w times by 2u squared cos squared theta over cos theta, and then take away this gw squared at the end. So I'm just multiplying my three terms by this denominator there. That's kind of what I'm doing. I know, again, I made a bit of a mess of this. I'm actually just gonna, do you know what I'm gonna do? I'm gonna move this all downwards. Let me just make my writing smaller. Because you could get asked a question, a show that question, where you've got to find another trig identity, or you've got to use another trig identity. Just move this up here. So what you're going to get, and I'm now going to do this in green actually, just to be really clear. So you're going to get the h2, so h2 minus h1 times by 2u squared cos squared. So that's our left-hand side, is equal to, now this first fraction here. So notice you've got a cos squared over a cos there. So that cos will just cancel out with that cos there. So you're going to get, so just rearranging that, like what we've got here, it's got a number 2 there. We've got a sine theta there. We've got a cos there. And we've got a w and a u squared. So I'm just going to write w u squared. So 2, we've done the 2, we've done the sine, we've done the cos, we've got the w, and we got the u squared. And then take away this g w squared at the end there. Now notice, remember our double angle formula. So remember that 2 sine theta times cos theta is equal to our double angle for sine, so sine 2 theta. So remember that. So what we're going to have here, I'll just write this down here, is that h2 take away h1 times by 2u squared cos squared theta is equal to wu squared, so wu squared there, and then 2 sine theta is equal to, 2 sine theta cos theta is equal to sine 2 theta, so a double angle for sine, take away g w squared. So you could be asked for this kind of equation as well, instead of the one that we had before. So just be aware of this too. So I know, again, this slide here was a real mess, but I just thought it was important that you guys can see that trig identities are really important in these projectile questions, especially the show that projectile questions, where they say show that this result is true, show that this result is true. So again, this equation that I've boxed off in red there is true for every projectile. Don't learn it, it's too long, it's too horrible, but I'm just showing you the process of how you can derive these complex equations. But these equations here, if you really want to, you can learn, for example, the maximum height. So the maximum height above the ground is u squared sine squared theta over 2g plus your initial height. Or you could learn this one as well. So the time it takes to get to your maximum height is u sine theta over g. The final speed of a projectile, so you can learn this one as well. So again, let me be really, really clear about this so you guys can see the clear formula. So that's going to be final speed. So final speed is equal to the positive square root of u squared, take away 2g, times by your final height, take away your initial height. And obviously, as well, at the end here, these 4 kind of refinements that you can make to make your projectile questions more realistic. So any questions, do drop them in the comment section below. Hopefully that is all clear. Again, you don't have to learn all these formulas, and I don't want you to, especially 2 days away from the paper 3 2023 exam. But if you can follow what I've done in that in all those examples, then that's really good, because that means you understand projectiles very well, and you should be fine with the projectiles question coming up. So thanks a lot for watching and good luck with your revision.